Okay, take a look around you right now. I'm willing to bet you're just a few feet away from one of these. The humble power brick. It's the one piece of tech we all have, but let's be honest, we never really think about it. They just kind of work, right? But how? Well, today we're going to crack one of these open, metaphorically speaking, and show you the incredible, invisible engineering that makes our entire digital lives possible. I mean, seriously, have you ever held one of these when it's charging something, felt it get a little warm, and just wondered, what is happening in there? It is so much more than a simple wire. It's basically a miniature, highly sophisticated power plant, and it's performing a whole series of complex transformations at lightning speed. So we're going on a little journey of power. We're going to follow the electricity from your wall outlet through this gauntlet of challenges packed inside this tiny adapter, all the way until it becomes the perfect, custom-tailored power your phone or your laptop needs to actually survive. So let's dive in. Our journey begins with the very first, and maybe the biggest, hurdle. The power that comes screaming out of your wall socket is, well, it's wild. It's a really powerful alternating current, or AC, where the electricity is just flowing back and forth, super fast. And if you fed that directly into your phone, oh, you'd have a very bad, very smoky day. Our devices are delicate, you know? They need a calm, steady, one-way stream of direct current, or DC. But just flipping a switch from AC to DC isn't nearly enough. A simple brute force conversion is actually really messy. It would try to draw power from the grid in these ugly, distorted spikes, creating a kind of electrical pollution that can mess with other devices on the same circuit. No, modern electronics have to be much, much smarter than that. Think of it like this. It's the difference between drinking politely with a straw and just gulping water from a fire hose. On the left, you see what a simple converter does. It just chugs power in these really inefficient spikes. But on the right, a modern adapter uses something called power factor correction, or PFC, to sip power cleanly. It actually shapes its current draw to be a perfect sine wave, perfectly in sync with the grid's voltage. You know what that means? To the power grid, the device looks like a simple, well-behaved resistor. It's a good citizen, making sure the power lines stay clean for everyone else. But all this sophisticated power processing, happening thousands and thousands of times a second, well, it comes with a major consequence. When you cram all this high-power work into a tiny sealed plastic box, you generate an incredible amount of waste heat. And this right here is a typical danger zone. 150 degrees Celsius, that's about 300 degrees Fahrenheit. That is the absolute maximum safe temperature for the tiny electronic switches, the little MOSFETs that are doing all the heavy lifting inside. Any hotter, and they just fail. So, with no fans and no vents, how on earth do engineers prevent a total meltdown? Well, they use this brilliant analogy, a conceptual tool that is literally the cornerstone of thermal design. They pretend the heat is electricity. Engineers build what's called a thermal circuit. Now, in this model, a difference in temperature is treated just like voltage. The flow of heat itself is treated like current. And anything that gets in the way of that heat flow, the plastic case, a layer of thermal paste, the heat sink, that's all treated as thermal resistance. By doing this, they can use the same math they use for electrical circuits, like Ohm's law, to calculate the exact temperature at every single point. It lets them design a precise escape path for the heat, ensuring that tiny silicon chip never ever crosses its thermal red line. It's genius. Okay, so after taming the grid's wild AC power into nice, stable DC, you might be surprised to learn that sometimes the very next step is to turn it right back into AC. Yeah, really. Think about things like high-performance motors or sophisticated audio equipment. They don't want the grid's AC. They need their own perfectly crafted, custom-made AC sine wave. And this presents a fascinating new problem. How in the world do you create a perfectly smooth, beautiful sine wave when the only tools you have at your disposal are simple digital switches that can only turn fully on or fully off? Because at its core, this is all a switch can do. It can turn on, creating a voltage. It can turn off, creating zero voltage. The result is this, a harsh, blocky square wave. Now think of a square wave like a musical note played on a really cheap, broken instrument. Sure, you get the main note you want, but you also get a ton of harsh, buzzing overtones. In the world of electronics, we call those nasty overtones harmonics. And this is the goal. This is what we're after. We need to get from that crude, noisy square wave to this pure, clean sine wave, with none of that extra harmonic noise. And you can't just filter out the noise. It's way too strong. Instead, engineers use a technique that honestly feels like a magic trick, a way to cancel out the noise before it's even really created. It's called harmonic elimination. Instead of one big, dumb pulse, the engineers chop it up with these strategically placed, precisely timed notches. By controlling the exact width and position of these new pulses, they can actually cause the most troublesome harmonics to literally cancel themselves out. You're not filtering the noise, you're shaping the waves so the noise is never strongly generated in the first place. It is the electrical equivalent of preventative medicine, and it's what allows for incredibly efficient and clean power. So, this brings us to the final universal challenge for pretty much every modern electronic device. All of this high-speed switching, whether it's for the PFC circuit or for creating those sine waves, it all creates its own kind of pollution, high-frequency electrical noise. This is the classic example. You plug in a cheap phone charger, and all of a sudden your AM radio, if you still have one, is just filled with static and buzzing. What you are actually hearing is the raw, untamed electrical noise radiating out of that charger and into the air. That electrical static is called electromagnetic interference, or EMI. It's the unavoidable byproduct of switching power at these super high frequencies. And this noise doesn't just stay inside the box. It travels down the power cord and it radiates through the air, just ready to wreak havoc on any other electronics nearby. Because of this, every country has really strict regulations on how much EMI a device is allowed to pump out. So how do you contain it? Well, you rely on one of the great unsung heroes of the power brick, the EMI filter. This is what the electrical noise coming out of a power converter looks like without a filter. It's an absolute mess, a total cacophony of interference. You can see those jagged spikes are way, way above the legal limits. This is enough noise to cripple any sensitive radio communication nearby. And now, look at the effect of the filter. It is just dramatic. The noise has been completely squashed, sometimes by a factor of 1,000, bringing it safely way down below that regulatory red line. And here's the crucial point. That EMI filter, which can sometimes take up a full quarter of the entire volume of a power supply, isn't just some afterthought. It is a critical gatekeeper, making sure your device plays nicely with the rest of the electronic world. So let's just recap this amazing journey for a second. From taming the grid's wild AC power, to managing blistering heat using these clever thermal circuits, to crafting perfect sine waves out of simple on-off switches, and finally, silencing that invisible storm of electrical noise. All of that is happening inside that little black box you probably never gave a second thought to. It's a testament to decades of brilliant engineering, making the impossible seem totally effortless. So the next time you plug something in, just take a moment to appreciate the silent, sophisticated dance of power that's happening inside. It really is the hidden engine of our modern world. And it just makes you wonder, what new technologies will this mastery of power unlock for us tomorrow?